earlier known as Indian National Remote Sensing Award, which is conferred by Indian Society of Remote Sensing for significant research contribution in the area of remote sensing, data integration, and modeling for geological hazard analysis in the year 2007. There are many awards and honors to his credit, owing to his outstanding research and research findings and publications as well. I think that's more than enough to introduce him. He has supervised PhD thesis, quite a number. Also, he's peer reviewer for multiple international journals, and he has been the invited guest for across the globe. So we are really fortunate to have Dr. Champati Ray sir as the speaker for today's session. Thank you so much, sir, for sparing your valuable time. May I request you to kindly start the session? Thank you.
So thank you, Dr. Abhijit and Dr. Deshpande sir, for this wonderful opportunity. First of all, I would like to thank both of you for this opportunity and introducing so nicely. But the main thing is that I am a simple worker working in this field and trying to address the basic problem what people face in the hilly area. And since it involves about saving life and property, so we try to do the what is really required on the ground and using remote sensing technique. So the basic idea is that to provide some kind of a information and solution which people can use it. So that's the whole idea. And I'd like to now share my PPT and. So, right. I hope the PowerPoint slides are coming. Yeah. Right. So, some of the emerging issues on the landslide hazard mitigation, I would like to refresh your mind. Some of you may be knowing about it. Landslide hazard assessment, in the country, it started like a supply-driven approach. That means those experts who are working on the landslide hazard zonation or the landslide hazard assessment, they started working on it. And initially, people were not very much aware of the landslide problem. Only the experts knew about the problem and their effect on the environment. But gradually, as the development started taking place in the marginal lands, particularly the steep slopes of the hills, then the people also experienced the problem. And since they experienced problem, there was a greater demand that how can we mitigate the effect of the landslide when we are constructing a house or a road or a tunnel or a dam. So that is how it started. And in several occasions, it has been observed that in the Himalayan terrain, the death and the loss of property is so high that on the global map, it has emerged as the hotspot of landslide on the global map. And most of you are from the Maharashtra, and in the Western Ghats, also we have numerous landslides during the monsoons on the western side and also on the eastern sides, many cases, like what we experienced a couple of years back near the Pune. So it has been observed that out of around 30 states, we have 22 states which are affected by the landslides. It is more so because of the developmental projects are getting affected. That's why more and more people want solution to the landslide problem. So that is how the whole thing, which started as a supply-driven approach, now it has become a demand-driven. And now the climate change impact and the developmental issues, as I said, these have come a long way to exaggerate or to make us feel the effect of landslides much more than before. So Himalaya, apart from the it has become the hotspot. Now the hotspot is not only due to the developmental activities, but also due to the tectonic activities. Now tectonics and erosion So you know, the Himalaya has been formed by the mountain building process, which is associated with the plate tectonics. And this plate tectonics, the Indian plate is subducting under the Eurasia plate, and because of that, enormous amount of pressure it puts, and the mountain is rising. And since the mountain rises, we have the slopes getting destabilized, and landslides, as a result, landslides happen. Now, this relationship is very interesting. Why this is interesting, I'll just explain in a moment's time in the next slide. So we will move on to that. Then the landslide development, society interaction, the climate change. So the extreme rain and rain in place of the snow, what is happening these days. So that is creating problem. So the slopes, which were reasonably stable under the snow condition, but they are not stable if in place of the snow we have the rainfall happening. So such kind of things we are seeing more. So what is required is a more holistic earth system science view is required. We need to take the whole thing. We have to see in the totality from the geological point of view, climate and the erosion point of view. Plus we have to see the human interaction in the form of the developmental projects being undertaken. And what is required is what is felt by people, that what we require is a something like a very simple people-centric landslide hazard mitigation program, where people can participate, government agencies can participate, and together government agencies and people together, they can solve the landslide problem to a greater extent. So this is what is a requirement, and some experts think that only the government action is required to mitigate, but government action is not sufficient. You know, government have a very limited role to play in the far-flung areas of the Himalaya. Most of the places are actually not known to the many, not accessible to government agencies during the time of disaster. So those people who are living there, their life is associated with the mountains, and they live there, and they are the first responder of disaster. So we need to have some kind of a holistic approach in which the people-centric the approach should be envisaged or should be developed, so that that can that can solve most of the problem. Now nowadays, as you are exposed to the remote sensing techniques, nowadays, because of the unmanned aerial vehicles, or the popularly known as drone, so a lot of remote sensing data can be acquired within very short time. And as you know, the landslides can happen anytime. It can happen in night, it can happen in day. Now quickly we need to acquire the data. Sometimes the satellite may not be available. So the whole idea is that we should be able to deploy the unmanned aerial vehicles, or the drones, to map the landslide or tell us the areas where the indication of landslide is observed, so that the the preventive measures can be taken up. And another one is nowadays the technology is developed for very high resolution deformation monitoring using subsurface probing. So this is a new area of research. So what we try to look at the below the surface. So what is happening below the surface? So whether we can monitor those the deformations linked to the surface and below the surface, because landslide is essentially a phenomena which start at couple of meters below the surface. And now technology is available, so we can measure it, we can monitor some of the deformation, and idea is that this thing also should be integrated in our mitigation strategy. But unfortunately, I can say that very few people, or the expertise is very limited to few agencies. In fact, even count them on the fingertip that who can do this kind of work. So luckily at IIRS we have developed this expertise, and we can deploy some instruments, and also we can do the survey of the landslide, and we can know what is happening below the ground. Now, what is the need of the hour, which is the focus of this lecture? Landslide early detection or the early warning and low cost preventive measures to contain the landslide. Why I use this word contain, not the control? The whole idea is that we cannot really, to control a landslide, huge amount of money is required, effort is required. So contain means minimum interference with the landslide, and so the cost will be minimum, and we try to live with the landslide, and so that it will have a much more cost-effective solution than very highly prohibitive curative cost. So aim is, can we really achieve the zero casualty status due to landslides, as we have almost done so in case of the cyclone? So as you know, in case of the two cyclones, Philin and Fani, the death toll was very, very low. It was in double digit only. Whereas the previous year's cyclone, we used to see large number of people being killed. And recent cyclone, even though the preparedness was not very good for the West Bengal government, still the death toll is relatively less. So that shows that the early warning system, what is developed by the various research agencies in the country, that have provided a lot of input, which has gone successfully into the management of the cyclonic disaster and reducing the death toll significantly. And the same can be envisaged for the landslides. So the point, what I was highlighting, the relationship between the tectonics, erosion, and the climate, ultimately leading to the landslide, I will try to explain with this very nice, simple diagram. So tectonics, that deals about the crustal thickening, and some kind of isostatic upliftment is happening for where the Himalaya is standing today. And the moment you have the the mountain standing, that will stop the the monsoon cloud, and it will induce the orography, will induce the rainfall. So that more rainfall, then we'll have the more erosion, and because of the climate change, we also have more rainfall now in the hills during the monsoon time period. So it is not the overall precipitation which has gone up, but the monsoon time period, the precipitation has gone up, and more so that within few days of the monsoon, a lot of rainfall occurs. It is not spread equally throughout the the 90 days or 120 days of monsoon. So that is a problem. In India, the monsoon rain all happens within a couple of rainy days. It is not well spread. So that phenomena is known as the intensification of monsoon, which is a lot of scientists are studying, and they are observing that within few days we have the most of the rain occurring, and either in the plain it goes up at the runoff, whereas in the hills, that is the one which causes before it before it goes off through the river system, and that causes landslides. So, and this phenomena, the moment there is a landslide, the mass will be reduced on the top of the mountain. The moment the mass is reduced, then the isostatic will be disturbed, and again the mountain will go up. So this is a geological phenomenon called the isostatic adjustment. So because of that, so the moment there is erosion, the moment there is a mass reduction on the top of the mountain is likely to go up. So this is a very unique geological phenomenon which is experienced in the Himalaya and many of these mountain in the tall mountains in the world. So the erosion, the moment the erosion happens, mountain goes up, and also we have, because of the plate tectonics, mountain is going up, and the moment the mountain goes up, you have the more orography, more rain, and more rain, that leads to again more erosion, more landslide, and again the mountain goes up. So the whole process is in a cyclic manner. The end result is always the mass wasting and the landslide. So you can see how interesting is this, that the mountain is going up and up, erosion is happening more and more, and landslides are happening, and more rain is happening. So this is a cyclic process. So we have least control on that. So that's the reason I said that better we live with the landslides than trying to completely control. And as much as possible, we should not disturb the slopes which have been developed over over last several hundreds and thousands of years. So these slopes, Himalayan slopes, or the slopes anywhere in India, actually in a quasi-stable condition. If you disturb them, so you may not know actually you have disturbed. Suppose you cut the trees today. So for immediately 1 year or 2 years, there may not be any problem because roots are still there. Once the roots are completely decomposed, then there is no binding material available and the landslide will happen. So the sliding will happen after a couple of years. That's the reason people don't realize that the effect, what they caused today, after a few years only, they will see the result. So because of that, the cause and result relationship is very poorly understood and poorly established. So that's the prime reason that why landslides are happening at many places, and we feel sometimes we are clueless. But if we analyze in a holistic manner, we will understand that there is an element of human interference, and there is a influence of the climatic factors, intensification of monsoon. Even if there is no tectonics involved, in some of the places why I'm telling tectonics are not involved, because in the the Western Ghats and other places there is no active tectonism as such. Tectonical features are there, but but the active tectonics is not there except the Himalayas. So still we have their landslides. So that's the reason the role of erosion, tectonics, and climate is variable, and this affect the landslides. Using the space science and spatial information, a lot of information is collected. So what we see that 10 important things I have shown here. One is the mapping of active and old landslides, mapping of causative factors, then identification of landslide hazard zones, deterministic modeling and factor of safety calculation, which are regularly done at IRS, and the slope deformation monitoring using differential interferometry, SAR, slope deformation using global navigation satellite system, slope monitoring using terrestrial laser scanner or the unmanned aerial vehicle, subsurface probing by geophysical techniques, monitoring performance of slope stability measures, then the early warning or detection system. So first couple of things are done regularly at IRS, and remaining ones also we have experimented, and it's quite possible to do, but although we don't do it regular basis, as and when opportunity comes, we try to do that. So to show you the landslides in different geological setting, the first diagram what I am showing you is the one which is linked to the some kind of a erosion, and you can see there's a river actually flowing here near the this is part of the near Dehradun in Himachal Pradesh. It's around 100 kilometers from here, and because of the bank erosion we have landslides happening there. Then on this side we have the Badrinath road which is going, because of the road expansion, a lot of toe erosion has happened, and because of that we have also the landslides. Then on this lower left side, because of the climate change, the area is very close to Badrinath because of the climate change impact. So the places used to get only snow, but nowadays we are getting rain. So because of the raindrops hit the ground with a large amount of the kinetic energy. So that displaces the sediments. Eventually that leads to landslides. The fourth one on the right lower part is very interesting, the Tehri Dam. So due to the high fluctuation of the water, due to the drawdown, which is part of the design, that water level will go up and go down because of power generation and storage of the water and power generation. So this fluctuation actually leads to some of the slides all along the rim of the reservoir. So reservoir rims are also prone to landslide, which I can attribute to the, so two here I am attributing to the the road construction and the dam construction. I attribute at the one of the these are also the some of the causes linked to the developmental activities, and another two are natural causes. One is the climate change impact, another one is the river bank erosion. So different reasons for the the landslides to occur in the Himalaya. I'm focusing on Himalaya, but some of the things you can translate also into Western Ghat and other parts of the country. So we try to attempt that can we really get some early information or early indication about the landslides. So we know that the rainfall is the main issue. Rainfall, the amount of rain, what happens within short span of time, a lot of rain goes below the ground, and we have some kind of a pore water pressure rise. So because of the pore water pressure rise, we have the slides. So indirectly, rain is linked to the landslides, and that's the region that monsoon time we have a lot of landslides. So we try to install automated weather station, and which will give us rainfall data every 10 minutes, and these data sets are collected. Then we try to do some kind of modeling that how much rain has happened in say last 3 days, and leaving aside the 3 days, how much rain has happened in the previous 15 days. So why we take this 15 days and 3 days rainfall? Because 3 days rainfall, that will have immediate effect on the landslide, and 15 days rainfall will have a effect, long-term effect. That's the reason why 15 days and 3 days rainfall are taken. And when you plot that together, and we see most of the landslides days, they fall in this area, in this graph, and particularly they're diagonally points are distributed. As you move diagonally from the x-axis and y-axis, one axis represents the 15 days antecedent moisture or the rainfall, and the 3 days rainfall on the y-axis. So as we go away diagonally from this, that means we move towards higher values of 15 days and 3 days time period. We have seen large number of landslides occurring. So we have diagonally, perpendicular to that diagonal line, we have drawn some lines, and we have found out the equation for the lines. Essentially, when we cross these lines, we are expected to see more number of landslides. So this is based on the 20 years of rainfall data and the landslides which have occurred. So Border Road Organization, which is responsible for the road construction in the neighboring in the border areas of India, they provided this data, and we have developed the model based on that. So now I will show you very interesting that this the threshold, what I have shown here, calculation of the threshold, we call it T6, T3, T1, T10, like that. So T10 is a higher threshold, T6 is a lower, and T1, T3 essentially can cause 1 or 2 landslides, so we ignore it. T6 can actually cause 5-6 minimum landslides, so we don't ignore that. T6 onwards is very important. T6 and T10, definitely the moment the T6 and T10 exceeded, we see large number of landslides. So one such occasion I just want to bring to notice in 2013, when the Kedarnath disaster happened, the intense monsoon, intense rainfall had happened for 3 days, and we tried to see how much was the the threshold in those days. So we found the threshold has crossed almost 400 millimeter. Normally in this area, Kedarnath area, more than 100 can cause landslides, but it actually had crossed 400, the threshold, which is a combination of 3 days and 15 days previous rainfall. So this indicates that there was a significant rise in the threshold, which is essentially that reflects that is a moisture condition significantly went up during 3 days preceding that event, which the event during which Kedarnath disaster occurred, and almost 10,000 people, 5 to 10,000 people lost their lives, and damage, across large tract of the river valley, and many places had happened because that the monsoon rain what we had was widespread. So extreme rainfall event was widespread. So that's the reason that we have large number of landslides here and there, and which is very well captured by this rainfall, by this threshold modeling. So we expect something like 100 millimeter, but finally we get a rainfall of 400. So that is a threshold, which is a combination of 3 days and 15 days. So you can say 4 times increase had happened. So that shows that this kind of rainfall threshold works, and it captures the extreme rainfall events, which are most important to understand the landslides. So not only at Kedarnath, at Badrinath also we had the opportunity to study the data. The similar thing is also observed at the Badrinath. So as I said, the entire Uttarakhand, 5 districts of Uttarakhand got affected, and Badrinath, Kedarnath was the 2 important places where a lot of people are stranded due to this the disaster. Now, just to show that Kedarnath disaster, you can see this is the satellite image of the Kedarnath, and this brown, if your color is okay on your monitor screen, the brown color indicates a lot of these avalanche tubes got activated, and through which landslide material came during 2013 disaster. This material actually came and buried the existing channels through which the water used to flow. When those were buried, so the water could not flow, and there was a small lake here, which is Chorabarita Lake, or the people also call it Ganga Sarovar. That lake also breached because suddenly there was a small, avalanche or a landslide. We have evidences of both. So that caused this, the water to exceed the volume immediately. So because of that immediate impact, so the lake breached, and the water, while started coming down, it could not follow. It could not flow through the existing channel because they were all buried by the landslide material. So the entire amount of water had to flow through the temple area. So which killed actually, minimum 5,000 people, and it can go up to 10,000 or so. Various figures are there because all the skeletons could not be taken out, so we don't have the actual death figure. And so this is one example that how the landslides could be mapped and which have played a role. So till now, people think that the Kedarnath disaster happened because of the Chorabarita lake outburst, but the lake outburst wouldn't have caused so much of damage unless the landslides would have taken wouldn't have taken place, which actually buried the river channels and didn't allow the water to flow through river channel. As a result, all the water had to flow through the temple area, and that resulted in the high human casualty. And we also attempted some kind of a deterministic modeling, so using the physical properties of the material, and we try to find out at for a certain area, so exactly how does the moisture, how does the the pore water pressure develops below the landslide, and we could simulate that. And for a particular event in Uttarakhand, which happened in 2009, that killed 43 people, and we have the rainfall data. You can see the rainfall threshold. What I showed is not a very simple thing. Now you see for the equal amount of higher rainfall, the landslide didn't take place. Particularly during the dry season, the moisture is absorbed by the soil because of prolonged dry period before the monsoon sets in. And particularly after the full swing, the monsoon was in full swing, then the moisture content, this brown line, moves in tandem with the rainfall, and that is what actually caused the slide. The day the landslide happened, that is the day the moisture content was also highest. So that shows that the moisture content which happens below the ground plays a significant role. So now coming to this, what we discussed about the landslide early warning system framework. So what should be done? So we have seen that we can do several models. We can estimate the. I'll just go back to show you that now in this kind of model, if I know the tomorrow's rainfall, actually I can calculate the threshold for tomorrow, and then we can issue a warning whether tomorrow landslide is expected or not. Similarly, in this case, with respect to the rainfall, we can make the model, and if you have again tomorrow's rainfall, the same rainfall can be considered, and we can know what is the chance tomorrow we will have a the big landslide based on the rainfall pattern. So that shows that there is a potential. We can know the landslide beforehand, and if we are able to predict the rainfall. And nowadays the weather forecast has improved a lot, although in the hilly area a lot of improvements are still required, but reasonably it is much better than in the past. And many occasions we see the rainfall, particularly the extensive rainfall, the extreme events which are extensive, they are very well predicted. 2013 the event was very well predicted, and so also recently also I have observed many occasions the Indian Meteorological Department has very successfully predict the precipitation. I will not say that every time the prediction is very true, because when it is a very localized phenomena or the phenomenon, these these cannot be, or it is difficult to the forecast, and unless we do that we cannot actually run this this kind of models. So this is the basic the premise of the model is that we need to know the rainfall, and if we do not know the rainfall, there are other models we have to depend on. We have to look at the physical the deformation on the slope, so that is also possible, and remote sensing techniques are there. You can see the things breaking up, and then the local people can be alerted. So the whole idea is that we can think about it early detection or early warning system. So that is the the whole background of this lecture, and I want to convince you that yes, early warning system or the early detection system is possible. So we can set up automated rain gauges which tell us how much rain is happening. So these are very cheap these days, and you can install automated weather station or automated rain gauge ARG. They're much cheaper, and in the hills, different slopes, it can be installed, and we can use the GSM network to access the data from remote places, and we can calculate the 3 days rainfall, 15 days rainfall, and accordingly we can establish the formula for the different regions. So areas which are more vulnerable, there the threshold will be much less. Areas which are less vulnerable, threshold will be high. So it has to be locally worked upon. Landslide inventory and preparedness, preparation of the landslide hazard prevention maps using remote sensing GIS is very essential, because we need to know which areas are more prone to landslide, which areas are less prone to landslide, and that is possible using remote sensing data products. Deformation confirmation by DinSAR or the SBAS or the PSNSAR, GNSS, new systems are there. So we can detect some kind of deformation. We can confirm that using these techniques. Landslide rainfall threshold relationship and intensity duration relationship. Another thing I did not discuss about the relationship between the intensity and duration of the landslide. What is the intensity of rainfall? How much millimeter per hour? And for how long it has been raining? So these parameters also can be considered before a landslide occurs. Use rainfall prediction and estimate landslide probability for different zones. This is what I discussed. And issue of the early warning as and when required. The moment the threshold goes up, it's so simple that we the warning is issued. Use debris flow, rockfall modeling for the the flow path run out. And very interesting this part, because the local people are living in the hills, and the landslide doesn't happen all of a sudden. There are always early indication. It has been observed that before 1 day or 2 days, you will see some small boulders falling, small rocks falling, cracks developing. The moment we observe such cracks, unusual cracks and boulder falling and cracks developing, Immediately this can be brought to the notice of the qualified geologist. They can run a simulation model to see whether the landslide likely to happen. If that happens, which are the areas likely to be affected? And accordingly, the local people, some of the local people can be shifted to safety before the event. Near real-time monitoring using differential interferometry, SBAS, DinSAR, or the UAV-based monitoring. So these are the techniques. DinSAR and the SBAS techniques are the radar-based techniques, and it can find out subsidence of order of few millimeters from the space-based observation. And community satellite or the UAV-based observation confirmation is very interesting. That we have to have all the data products, all the techniques as community-based observation. Also, people can be told what to observe, how the deformation is happening. They should be trained, and it's not very expensive, and people are reasonably intelligent in the rural area where they live with the nature, so they can tell the cracks when the cracks are developing. And UAVs we can deploy, we can look at satellite data to see some kind of deformation. So all that can be put together, because one option may not serve the purpose always. We have to have all the options so that we should not miss out of in a single landslide before it happens. Evacuation and strict vehicular traffic. So we know the landslide is happening, and many cases Uttarakhand, the vehicle can be stopped, evacuation can happen so that the precious lives can be saved. Then we should have a mechanism to take off the warning. Giving warning is is one thing, but at the promptly, the moment the situation improves, we should be able to take off the warning. And the one aspect about the detection, interferometry SAR, I am just showing you now 3 images. So that interferometry essentially deals with the 2 satellite images, and one acquired before the phenomenon and another one after the phenomenon. So what we try to see, is there any phase change? Microwave data actually measures the distance between the satellite and the object. So if the object has moved, if the place has subsided or it has little bit moved, the ground has moved because of the landslide, so immediately we will have a phase difference, and this phase difference we can multiply by the path difference, certain factor of path difference, and basically is a path difference which causes the phase difference, and we can have a relationship how much the phase difference and how that can be translated into path difference, and path difference will be translated into some kind of a movement. So we have taken data of 13 April and 22nd June. We see some fringes starts appearing that indicate some kind of movement is happening. 22nd June and 27th July, which is the beginning of the monsoon, we see good amount of movement. Then 13 April to 27th July also we try to see, but this is the gap increases between the 2 data sets. So because of that, we start losing the coherence and we don't see it so well, the deformation. So what we are seeing, the almost a month, more than a month wide gap data set we are looking at it. But now the Indian mission, new mission which is being launched, will be launched very soon. This is called the the NASA ISRO mission. We call it DinSAR. NASA ISRO satellite, the synthetic aperture radar DinSAR mission will be launched. So this will reduce this date of what I'm seeing you showing you here, almost a month gap, to 6 days. So we will have every 6 days and 12 days interval the data. So that means we will have less chance of loss of coherence, and if there is any movement, we should be able to detect movement, because we'll have a L band and also the L band and the S band. Different frequencies are being planned. Different frequencies, different incidence angle are also. The satellite path is being managed such a way that every 6 or 7 days we should have a data acquisition, and eventually it will help us to monitor this kind of changes. And before the ground moves, the changes what I am showing you here, one fringe, actually we have used the C-band SAR data. One fringe indicates here this is something like half of the wavelength. And so that is 5.6 centimeter wavelength. So if you take the one color fringe, that is half of the wavelength, it will come down to 28 millimeter. So you can count the number of fringes multiplied by the 28 millimeter. So that will give the total subsidence, along the line of sight of the satellite. So the moral of the story is that few centimeter of movement, so 2 centimeter, 3 centimeter, maybe 4, 5, and 10 centimeter of movement can be detected through satellite. So when you detect, the couple of centimeters, then the actually landslide has not taken place. Only the initial movement has taken place. So this is what I call the early detection. And not only the interferometer SAR, what I have demonstrated, we have also used other techniques, UAV based techniques and other techniques to map this early movement. So we will see also on some of the more slides. So this is the terrestrial laser scanning. This instrument we have at IRS, and using this instrument, the landslide has been monitored. One important landslide, we call it Kaliasur landslide. It is on the way to Badrinath and Kedarnath. And this landslide was monitored from 2 different angles, and then we have generated the 3D. This 3D tells us about the the terrain topography, and if there is any change. If we take data on day 1, again we take data up to 10 days, and if we see any minor changes, then we should be alerted that some kind of movement is taking place, and we should try to further investigate before issuing the warning. It's very interesting. The one town is there, Joshimath in the Uttarakhand, on the way to Badrinath. And this town, at several places, it has developed cracks on the roads, which are essentially due to the landslide or the movement of the ground. It is so slow movement that it takes 3 to 4 years, sometimes 2 years, to develop cracks to appear on the ground. And so this is also can be before the devastating landslide, some kind of a subsidence, some kind of a ground deformation will take place, and this is, we must detect this, map this, monitor this. So once we see a lot of deformation, then we should be alerted that movement can take place anytime, and then accordingly we should be prepared. So this is how we have tried in the same town. Very meticulously we have tried to find out which are the the cracks likely to move. Red lines are the active landslides. Anybody can go to ground and see, but these yellow lines are the one which requires some skill to interpret. And blue line is the road actually across these the sliding material. So you can see that roads, the area has been traversed by several roads and must have been affected. Roads must have been affected by these slides, and that is what also we have seen on the ground. And another example, I am showing the road construction or the widening of the stores, widening of the roads in in Darjeeling, Himalaya. There's a very nice heritage rail track is there. A lot of Hindi movie they have been shot, and very nice songs. You must be remembering the old, the songs are, they have been shot over there. But that railway track is no more. It is mainly affected by 2 landslides, and we went there to see. And these 2 landslides have happened, in the recent time. So 2001 image I am showing. This is the place. There is no sign of landslide. Now I will show you the next image. So this is 2008. So between 2001 page up, I'll just go 2001 and 2008. How the landslide starts appearing, and by the time 2011, 12. So the amount of landslide which has happened is huge. So, and this is, there is, so this shows that the landslide monitoring is possible using remote sensing, number 1. Number 2, we can also review the road widening, what was going on there, how much it has affected, whether it was done scientifically, and whether it has any role to play with the landslide. So we cannot say all the landslide are due to the developmental activities. Always we cannot blame just like that, but it's a matter of investigation. Whenever there is a developmental activity very close to a place where landslides have taken place or likely to take place, these developmental activities need to be cross-checked. And I always call upon that cross-checking is not stopping the development, but only thing is that we have to have some avenues, some investment, such that the developmental work we undertake, which will be sustainable in near future. So another example I cite from the Nepal Himalaya. So it is not only the remote sensing helps us to monitor disasters within our country. This is a disaster which happened actually away from our international boundary. So landslide happened in Nepal and it blocked huge amount of water, and this water was about to be breached, and flooding was expected in the downstream areas of India. So we looked at the landslide, we calculated the volume, we estimated the water, and also we attempted to know if there is a breaching, actual breaching, how long water will take to reach Indian border. So this is basically remote monitoring is also possible. And these are the graphs which shows before the landslide how is the the water level and the discharge, and after the landslide you can see suddenly it had stopped water level and the discharge, and which went up because the blockade was removed with the help of the the army personnel. So again the water starts flowing. So the curvature what we see here, sudden decrease and increase, this is a signature in the entire water course. So looking at this, we can know that how much time it has taken to reach. So accordingly we can calculate. So this is what we calculated, that almost 24 hours we were getting early indication that if the landslide breaches is breached by the the lake or the reservoir, we will get 24 hours actually time before it reaches our border, and accordingly we can prepare our people for the evacuation and the preparedness, various preparedness actions. So to moving towards a zero casualty status, is it possible to do remote sensing based landslide inventory and deformation monitoring? We have demonstrated. I have tried to convince you it is possible. Historical satellite image based analysis for vulnerable slopes and preparation of the hazard zonation is possible. Early automated weather station installation and close monitoring of the vulnerable slopes, we need to do that. And at every AWS and vulnerable location, rainfall threshold should be routinely calculated based on the daily data and predicted rainfall data. Early detection of landslide using synthetic aperture radar, optical remote sensing, UAV, GNSS, the crowdsourcing, people-centric approach can help. Bottom-up approach, debris flow, rockfall simulation for all high-risk areas can be done. And drone TLS, terrestrial laser scanning, or the global navigation satellite system-based slope monitoring should be mandatory for all major projects. So this needs some kind of a policy guideline. And in Uttarakhand, since we are at this Uttarakhand region, and another important points are there. The mainstreaming disaster risk reduction and developmental planning using building, road, or hydroelectric project related construction as a mean of strengthening of slopes. Catchment and dam site monitoring for slope deformation should be responsibility of the the respective authority. Need a policy guideline. Because many times there is a people say that it is not our responsibility to maintain the slopes or the study these slopes. So developmental agencies, dam authority or the road agencies should look into the slopes, because the slopes are not stable. Their structure will not be stable. We need to have some kind of a paradigm change in policy framework. So construction at any site having slope more than 20 degrees, we should have slope stabilization measures with financial commitment. And the state should provide some kind of policy guideline, so that what I've hinted here, the construction at any site having more than 20 degree slope should have some kind of slope stabilization measures with financial commitment, and the people should adopt that. And government should set up a knowledge cell advisory body for the landslide or a landslide authority with statutory powers to undertake all studies related to the the landslides. Otherwise, we have seen experiences that so many agencies working but lack of coordination. We need a people-centric low-cost solution that can be educative and sustainably long future in the long run. So What are the main 5 takeaways from this lecture? One is the remote or the direct monitoring is possible using technology and society action. We can remove the excess water, there's a trench or interceptor drain we can make so that this slope is stable. Remedial measures for slope strengthening, netting, soil milling, rock bolting, then the reinforced concrete cement piling, benching, reinforce the river bank and retention wall construction, and revegetate the slope with bamboo or appropriate sites, appropriate species for the minimum slope, minimum erosion, soil loss due to erosion. This is one example how the pore water pressure is removed. There are several pipes you can see. There is a submersible pump is there. The moment water level comes up, immediately the automated pump actually works and takes out the excess water and area becomes safe again. And this is from Sri Lanka. That's the place where they have constructed this remedial measure. Automated extraction of the water is basically, there was a train accident and I think around 150 people had died at the site. So at the site they have developed this some kind of a measure which will reduce the pore water. So they don't allow landslide to happen in this area. And to excavate, to take out the excess water, this is the kind of drain. They have the drainage system which they have developed, because Sri Lanka, some of the areas get the rain due to the 2 monsoon. One is the southwest monsoon and northeast monsoon. So huge pipes have been laid alongside of the roads for the water to they take out the water so that it doesn't slope is not charged with too much of water and causes some kind of a landslide. So I'll just show you a couple of just one example maybe yeah, then before we close down on the earthquake induced landslide. Right. So we'll move on to another thing. So far we've discussed about the landslides caused by the the rainfall, but also the earthquakes. They also cause landslides. So we have experienced 2005 Kashmir earthquake, which was a 7.6 magnitude event and caused numerous landslides in the Kashmir area. And the causative fault could be mapped. And then what is important is I want to show you several new landslides which occurred. Reactivation of the low landslides also occurred. And all that actually created too much of trouble for the people living there. So destroyed the roads, it destroyed the many houses. So and we want to do, and this area is highly, not at all, and very limited accessibility is there. Remote sensing is the ideal tool to use for the mapping of the landslides, because that was also helpful for the reconstruction, rehabilitation in those areas. And I'll show you remotely. This is the POK region, and all these, the antisocial elements are there and difficult to go there. But using satellite data, we could point out how much mass has been removed from a landslide by natural process, of course, and how much has been deposited. So you can see the red patch is actually mass has been depleted, and blue part is where the material is, where material has been deposited. So, and here different colors indicate the old landslides, new landslides, and the reactivated landslides. So all that landslide related information could be obtained using remote sensing media for a very, very difficult area, which is the POK, and mostly, the Taliban and all those anti-social, I would say the terrorist organizations are, they have their camps there, and difficult to do the field work. So you have to depend heavily on these remote sensing data products. And there are techniques now using the Newmark model. We can actually say that how the slope is going to respond in the event of earthquake. So whether it will sec violently or it will sec in a gentle manner, but what is net impact on the slope stability? Eventually, it leads to landslides. That is what has been seen, and I have listed here how the model is to be done. Soil geology, friction angle, cohesion can be used to calculate factor of safety, and the INSAR or digital photogrammetry can be used to calculate the slope. This model requires a very good slope map, And then the seismic source characterization about the peak ground acceleration and all those stuff have to be known. But that the most critical part is the slope actually, and the geological factors. So in this case, we have shown one example where the friction angle, the cohesion, and unit weight. I think this is their three basic parameters, geotechnical parameters, civil engineers, you must be knowing, affect the slope stability. So based on this, we try to calculate the factor of safety. And this factor of safety, when we calculate, then we have to see that what should the factor of safety, so that in the event of a earthquake, landslides will not take place. So this is a factor of safety map has been prepared, and finally this is what is compared with the actual landslide due to earthquake, and we have seen that there is a good amount of correspondence between the actual landslides and all the model ones. Now, so far we have said about how the earthquake is going to cause landslides, but like rainfall. The question is, can we really say when the earthquake is likely to happen? Rainfall we are able to predict, and then we can predict the chance of landslide. But in case of the earthquake, and can the earthquake be some kind of a precursor or some kind of advance warning can be there? And we have been working on it, and it's very interesting. And although I don't want to discuss too much in this lecture, but we have seen, we have developed a technique. We are looking at the total electron content in the ionosphere. Ionosphere, that's around 300 kilometer, 90 to 400 kilometer up in the sky, and the electron density before an earthquake actually changes significantly. And this electron density is changed mainly in a systematic manner over the epicentral region. Looking at those, the anomalies, changing the electron content, actually we can calculate the location of the likely location of the earthquake. And this we saw that the before 4 to 5, before actually in this case we had earlier seen before 14 days, before 11 days, before 8 days, and before 1 day, the anomalous behavior of the total electron content in the ionosphere before the Nepal earthquake 7.8 magnitude on 25th of April 2015. And when we at the same time we took a lot of ground data. This first diagram is from the global data set. The ground data has been taken, and we try to see the anomaly was maximum closer to the epicenter. That indicates that we can know before 14 days or 15 days the event is likely to take place and where it is likely to take place. So this information, then we can calculate what is the chance areas will experience landslide or not triggered by the earthquake. So some kind of an early indication about, I will not say early warning system or a prediction system, because if you call it a prediction or early warning system for the earthquake, you have to tell about the magnitude, you have to tell about the exact time, and also the exact place. Since we are able to tell the approximate, the time and the place, so we are not able to tell in a deterministic manner. I'll call it the early detection or some kind of earthquake precursor study. So this precursor indicates that something is brewing, and earthquake can happen in a place which is plus or minus 50 kilometer, 100 kilometer. And but once we know that, we can run the model, Newmark model, and know which are the areas likely to be affected by the landslides due to earthquake. So these are all published literature. You can actually read these papers. So almost coming to the end, landslide hazard mitigation. We need to look at the comprehensive strategy, starting from the mapping, which we use the optical remote sensing, radar, ground-based observation, and monitoring, then modeling, and the policy. Finally, it has to flow into policy imperative. And the key points we should remember that landslide, we have to look at a earth system science approach, holistic climate, tectonics, erosion, and human interaction. We have to understand the whole thing. Development in hilly area can cause landslides, so we can do some kind of mainstreaming in disaster risk and risk reduction approach for the developmental planning. space and allied technology can make big difference. And like cyclone in landslide, we can aim for the zero casualty status. So with this, thank you very much. And I hope I have tried to convince you and that early detection or the early warning of the landslide is possible, and we can attempt that for the Himalaya or the any other places using a holistic mechanism where the space science and the community ground-based observation all can play a role. So thank you very much.
Thank you so much, sir, for the wonderful lecture on the landslide hazard mitigation and early warning system. It was a wonderful lecture with the comprising of the case studies as well as popular case study that is been sought for, that is the Kedarnath tragedy, and also comprising or consisting of two type of the rainfall triggered as well as earthquake triggered landslides. So we are really grateful for this lecture. Now, I think we can take for a couple of questions. Um, uh, um, I think there is a question. Sir, can we take the questions?
Yeah, please.
Right. Okay. So there is a question from, rather couple of questions from Walchand of Department of Applied Geology, NIT Raipur. That is asking that, is there any real-time monitoring system for landslide hazard in India? If there, how monitoring? I think that has been
Some
answered.
attempts, right. Some attempts have been made. There are a couple of case examples under the R&D. So one is the Amrita University in South India, Coimbatore. They have deployed, in a couple of places in Kerala, and that is one. That is purely instrument based actually. Second one is the Central Building Research Institute, CBRI, CSIR, at Rajkiy campus. In the Himalaya also they have a test site, and IIT Mandi also has attempted in a couple of places. So apart from these three, other governments, some of the agencies are trying, but there maybe at other places. I think Sikkim also, the Amrita University and some other organization, they have also tried. But there are very specific examples where people have attempted.
Okay.
But what we try to promote methodology which will work from the space based approach, and is something slightly different from the approach what they have been doing, which is ground based, instrument based, expensive, and operational issues are there.
Right. He further adds another question that there is development of lots of tunnels in Himalayan terrain. Can they become the reason for landslide, as extra peninsular India is more prone for landslide hazards?
The Himalaya area, yes, there are a lot of tunnels. The construction is going on. The whole idea is that it's very case specific, and the impact of the tunnel, particularly wherever they are passing to the vulnerable slope. So those areas they have to be very careful.
Okay.
So access tunnel construction, normally they also prefer wherever the hard massive rock is there. But moment they have the loose debris and the friable rocks, the tunnel construction is also difficult, and that is the place where the landslides likely to be encountered. So they have to be really careful. And what I trying to impress that because of the the landslides, we should not stop the development. Only thing is that remedial measures have to be factored in. So additional investment have to be made, in those areas. But unfortunately, what is happening? This factor is completely ignored, and as a result, we are paying heavy price later.
Yes, sir. Okay. There is one more question from Professor Radhakrishnan. He wants to ask that whether the uplifting and erosion are balanced in Himalayan terrain. If not so, what is the rate of upheaval and erosion?
The uplement rate is, it varies across the Himalaya and goes up to say 4 to 5 millimeter a year. And erosion is not quantified, very systematically, but I would say it's around 1 to 2 millimeter. And definitely, the more than the erosion is the uplement is high. That's the reason actually why we have a tall mountain. But erosion is catching up, and a lot of places where the sediments are lying, the morainic material, the glacier-borne material are there. Now we are going to experience rainfall in those areas. So these sediments are getting, activated.
Okay. So I think I have taken all the questions on which was there in the question and answer session. Okay, so thank you so much, sir, for your valuable time. I guess you were busy with some meeting and which you have postponed.
Yeah, I just go now
Thank you
immediately.
so much for such a kind gesture.
Thank you very much for listening, and talking to you.
Thank you very much.
Thank you. Bye bye. Namaste.
Bye bye. Namaste,
Thank
sir.
you so much. Thank you, sir. Okay, and now this is an announcement.